So far, the limits we've considered have been limits as x approaches some point on a graph. Another very common limit that was of interest to mathematicians and applied mathematicians is what happens to a function as x gets very, very large or approaches negative infinity, becomes very, very large and negative. We have a particular symbol for that. We write x approaches infinity, and the same kind of result is what we're looking for. We're looking for a single value, L, that we can say that f of x approaches, but might never quite reach, as x gets larger and larger and larger. Now there's some very, again, technical definitions about how we can represent this idea. It tends to obscure the meaning, though, sometimes. So we're just going to focus on the intuitive understanding of what happens when x gets very large and does our function approach some single finite value. All right. If we talk about, say, a function like e to the x, remember its shape is the exponential growth, like so. But what we'd notice is, if we drew it more accurately, is that the graph flattens out and has an asymptote. Now, e to the x is never equal to 0. It's impossible to put any value into this function and get a 0 back. So we're always going to get something positive back in the exponential curve because the y value is always going to be larger than 0. However, we can say that the limit as x approaches negative infinity of e to the x, if we follow this graph out further and further and further, what are we getting closer and closer to at all times? Or what can we get arbitrarily close to if we go out far enough? That's the real definition. Well, in the end, we can get as close to 0 as we like. So we say the limit as we approach negative infinity is 0. The limit in the long run, if we could go out as far as infinity, we would keep approaching 0. Infinities are slippery concepts. I'm going to try to be as technical about them as I can, but just beware of some of the common phrases we use with infinity are a little bit suspect. All right, what can we use this kind of result for? Well, let's talk about this graph here. The limit as t goes to positive infinity, notice there's no negative sign, of this function here. And in fact, this should look familiar. This is actually one we saw back in Unit 1. Well, as t goes to infinity, you can work your way out from where the t is in the function to ask what happens to the rest of the function. E to the minus 0.04 t, well, let's actually write this out as a formal limit for practice. The limit as t gets larger and larger, or heads out to infinity, of this value is e to the negative something very, very large. Or, like we said here, e to the something very, very large and negative will end up converging towards 0. So in fact, this limit would equal 0. The function heads towards 0, but in the limit we'd say the limit equals 0. And so our 15 minus 10 e to the minus 0.4 t, that's a perfectly nice function. And then we ask the perfectly reasonable question, what happens as t gets larger and larger and larger? What I'll usually do in notes is say, well, this function here, this part of the function here, is heading towards 0. That limit of that part of the function is going to be 0. And then, well, if that's going to be 0 in the limit, the 15 is going to stay the same. The 10 would stay the same. And we can basically apply this limit to each of the terms individually and see if we get a sane answer. And in this case, we do. The limit would be 15. Going back to the original function, what's that saying? Well, as t gets bigger and bigger and bigger, this function, this part of the function here, is going to get smaller and smaller and smaller. You're going to play less and less of a role. The 15 is going to be left there. 15 minus 1, 15 minus 0.1, 15 minus 0.001. And as t gets larger and larger, eventually you're going to be left with just the 15 in the long run. Or we can get as close to 15 as we care about. So that's one way we can see limits as x goes towards infinity, and they happen a lot. We reason a lot about exponential functions in particular using this kind of approach. Sometimes we formally use limits, sometimes we just say exponentials shrink towards 0 in one direction or another. Another common case is to study rational functions where we have a polynomial over a polynomial and ask what happens to that relationship, to that ratio, as x gets larger and larger. For those in computer science, these are everywhere in algorithm comparisons in terms of numbers of operations of one versus another method, and you ask what happens when our problems get really, really large. So in this particular case, I hesitate to say this, but you could try to say it this way. If we try to sort of plug in infinity, oh god, I can't believe I'm saying it. If you try to plug in infinity on both, everywhere we see an x, we would get an infinite value on the top and an infinite value on the bottom. This is known as one of the indeterminate forms. This infinity over infinity, it could be anything. It could be 1, it could be 0, it could be minus 20, it could be infinity. We don't know because we've got a number that's growing over a number that's growing. And so the answer to deal with this is we need to simplify before taking the limit. So the indeterminate form gives us no answer whatsoever. No idea. The limit might exist, it might not. This tells us literally nothing. As soon as we see this, we have to go back to the original function and deal with it as it was given to us. So what are one of the tricks that we can use? What is one of the tricks we can use for evaluating rational function limits? Well, we've got x squareds here, and they seem like they should cancel out. The x squareds are the most important terms in these two numerator and denominator expressions. So how can we focus in on those x squareds? Well, what we can do is divide by the x squared on top and bottom both, or multiply by 1 over x squared. So what we're going to do is add this ourselves to what we had already. So divide top and bottom, and in general, we're going to do this with the highest power of x that we can see. And notice that we haven't changed anything by doing so. We just multiply the top and bottom by the same thing. So that's equal to multiplying by 1, but it's going to give us a new form that'll be easier to work with. So we haven't changed it, we just have rewritten it. And then what we can do is simplify. So we still have our limit. We still want to know what happens as x approaches infinity, but as we multiply this in, we're going to have a 1 for the leading term here, plus 1 over x squared. And in the denominator, we're going to have a 2 minus 1 over x squared. And now, it may seem like a subtle difference at first, but it has a huge impact on the final calculation. As x goes towards infinity, now it's not the case we had before where the entire numerator went to infinity. Here, this expression 1 over x squared, 1 over 10, 1 over 100, think of larger and larger values of x, 1 over a million squared, that part is going to head towards 0, and a number like 0 plus 1 is perfectly reasonable. There's no infinities here anymore because we're dividing by those larger and larger numbers. Likewise, the x squared in the denominator down here is also going to get closer and closer to 0 as x gets larger. So by turning an x squared into a 1 over x squared, we've traded something that was an infinitely large value for something that is heading towards 0 and is much easier to manage. And in this particular case, because we have the 1 plus out front, we can simplify this expression down to simply 1/2. So the limit of this expression here as x gets larger and larger is 1/2. This function is getting closer and closer to a horizontal asymptote is what this would look like. And without knowing too much about whether it's coming from above or below, it's going to do something like that. It's going to converge gradually towards a y value of 1/2. And so that's what we can learn from some of these limits at infinity and what they tell us about the properties of a graph when x gets very, very large or very, very large negative.